So how do we use JavaScript as a secure object capability language? And what are these object capabilities anyway? For this part of the talk, we're focusing on that layer. So if you've thought that JavaScript cannot be used to write reliable or secure programs, I want to show you this counterexample. Throughout the talk, I'm only going to be making use of two main abstraction mechanisms in JavaScript, the function and the record. Over here, we have a function called makeCounter on the outside. And every time it's called, it creates a new record with an inker and decker method and a new count variable, which is effectively the instance variable of this object. The inker and decker are shown on the surface because they're visible outside the object. The count variable is shown inside because it's encapsulated. Only the inker and decker method can get to it. Every time we call makeCounter, we get a distinct instance, and each of these instances is isolated from the others. What can we do with this? Well, for example, maybe we want to keep track of the number of people inside a room by having an entry guard count up when people are entering the room and an exit guard count down when people exit the room. So we can give the entry guard access to the inker function and the exit guard access to the decker function. And the result is that the entry guard can only count up, the exit guard can only count down. So this gets at the core idea of object capabilities, which is a conventional object reference, familiar from object programming, is a permission. If object Bob does not have a reference to object Carol, then Bob cannot invoke Carol, cannot provoke whatever behavior Carol would have. If Alice has a reference to Bob, and Alice invokes Bob, passing Carol as an argument, then Alice has both used her permission to invoke Bob and given Bob permission to invoke Carol. So this is all familiar from memory-safe object languages. What brings us to object capabilities is when this is the only way an object can cause effects on the world outside of itself. In that case, the reference graph, familiar from the programming language literature, becomes identical to the access graph from the access control literature. It gives us a very natural way to express the principle of least authority, in which an object is only given that permission that it needs to do its legitimate job, such as giving the entry guard only the ability to increment the counter. And by giving objects very narrow authority, you deny them most of the opportunities for things to go wrong, for them to do damage if there's an exploitable bug. The fact that JavaScript can be used in this robust and secure manner is no accident. I joined the ECMAScript committee in 2007 when JavaScript was really a tremendously messy language. And we got all of these elements added to JavaScript, beginning with JavaScript strict mode and object.freeze in ECMAScript 5. We got all of these things added in order to enable JavaScript to be used more reliably and more securely. JavaScript, the language, has no I/O. It's essentially a pure computational language where all I/O, all ability to cause effects in the world, is provided by the host. And JavaScript has several very different hosts. Of course, JavaScript started in the browser. It's also now very, very prominent on single machine servers. It's also very prominent but not well known to be prominent in embedded devices. Probably some of the devices in your house are actually running JavaScript. And of course, now we're running JavaScript on blockchain. And what we're advancing is secure ECMAScript, is this secure runtime for enforcing the security properties needed to turn JavaScript into an object capability language. We have a core mechanism that works securely in JavaScript today, and we have a proposal before the committee that moves more direct support directly into the standard. The SES secure ECMAScript kernel that we have working today was done in a collaboration between Agoric and Salesforce, and Salesforce is using this on the browser to support a 5 million developer ecosystem. Some of the key elements of SES have already been incorporated into Node, and we're continuing to work with some key members of Node security to get more direct support for SES into Node over time. On embedded, there's now a standards organization, TC53, for standardizing the JavaScript for embedded devices. And that standards organization is explicitly standardizing on SES, secure ECMAScript, as the standard JavaScript for embedded devices. The main embedded JavaScript is the XS engine from Moddable. And that one, they already have a configuration out of the box that's directly an SES engine. Of course, Agoric is supporting JavaScript on blockchain. And we've been working with MetaMask. MetaMask, also on the browser, is a platform that people use to write user interfaces for interacting with distributed apps that run on blockchains to interact with smart contracts. And they've been using Browserify as their module system for packaging modules to run on the browser. They are now switching from Browserify to Sesify. They've built Sesify, which is a version of Browserify that has SES built in. So why is it that all of these different major players are putting so much effort into switching to secure ECMAScript? These are the packages that make up a MetaMask bundle. As run under JavaScript today, each of these packages, if it misbehaves, can completely destroy the integrity of what it's running in. And when MetaMask is being used to manipulate financial assets on blockchains, then if MetaMask is corrupted by one of these packages, then it can not only destroy the integrity of your user interface, it can steal your assets, the assets you're manipulating through that user interface. Now, I'd like to take like somebody in the audience to take a guess. Of the typical JavaScript application, how much of the code in the application is specific to the application, was written by the people putting the application together, as opposed to just linking in third-party libraries? Anybody care to guess? 5%. Okay. I'm actually very impressed at how accurate those answers were. NPM estimates that for the typical JavaScript application, the answer is 3%, which means 97% of the code that you link together to create an application is third-party code that you have little reason to have confidence in. And in JavaScript, as it's run today, every one of those packages is given all of your authority and can abuse anything that the application itself was given to manipulate. And we've seen these attacks. The attack called the event stream incident was a malicious upgrade of a package published to NPM that was specifically targeted for stealing the Bitcoin from those running a particular Bitcoin wallet. With SES and the way MetaMask is using it with their Sesify, they can lower their risk to third-party code tremendously. So the colors here represent a measure of risk. The purple dot is the package that is the only one that is unique to MetaMask. All of these others are third-party packages that are linked in, but the green ones are those that, after static analysis about what it apparently uses, is then run under SES in such a way as to be given only the authority that it apparently uses, and therefore, even if it's malicious, its ability to do damage is very little. The red, of course, are the real hotspots, the things that need a deeper security review. So why are they red? Let's mouse over that one. And we see that that one's red because it directly accesses the network. It uses XML HTTP request as a global variable. Therefore, in order to run this application, you have to run that module in an environment in which there is such a global variable that seems to be the global XML HTTP request object. And any security review should start with these hotspots, should focus the attention on these hotspots first. We can also explode this into a graph of modules with the import graph among the modules, where SES can constrain the import graph among the modules to only be within the package dependency graph among the packages. So how is it that we got from this tremendously messy language, JavaScript as it was in 2007, to the ability to use JavaScript securely in this way? Well, our approach has the slogan, don't add security, remove insecurity. So ECMAScript has some really terrible features that make secure programming impossible. So our first step was to define ECMAScript strict mode, which we got into ECMAScript 5, and that leaves out most of those problematic features and enforces that you stay within the strict subset. So we can take that off the table. ECMAScript strict mode still has some severe problems that prevent it from being used as a secure language. In particular, any code linked into a program can reach in to object.prototype.push and replace the push method, array.prototype.push, and replace the array push method with some malicious push method that all the other code inside that system is now misled into using. Also, JavaScript, as it's run today, there's a single shared global object that all code has access to, and that's where all of the host objects that lead to authority to the outside world reside. So these are the problematic features that we need to take off the table. We need to create a mechanism to enforce the absence of these features and instead program in a JavaScript in which those misfeatures are repaired. So that is secure ECMAScript. The good news is we had to take very little off the table in order to define secure ECMAScript. Secure ECMAScript is essentially JavaScript. The experience going back to the Caja project at Google from the 2007 timeframe, we found that a tremendous amount of old legacy code runs under SES. And today with Salesforce, with MetaMask, with Agoric, we're finding that as well, that a tremendous amount of old code will run under SES, and therefore we can use SES to bring these security properties. However, JavaScript is still a messy language. It's still a language that if you use the whole language, it contains many features that are hard to reason about. Double equals is infamous for having crazy coercion rules. So what we've done for our own sanity is defined a disciplined subset called Jessie that only has the parts of JavaScript that we know we can use reliably. And all the code you're going to see in this talk is in the Jessie subset, and most of the code we write at Agoric is in the Jessie subset. And that brings us to the end of that layer. And does anybody have any questions?
In what capabilities, in what capacity is Salesforce using it right now?
So Salesforce has what they call the Lightning platform. And the various applications contributed by third parties that you can select to create a Salesforce user interface. When you go to their essentially app store and pick the various apps and compose them, those are all running in SES. And the fact that the Lightning platform is enforcing that they run in SES means that the Lightning platform itself is largely protected from their misbehavior. And when you compose multiple of these apps together into one Salesforce user interface, those apps are largely protected from each other, so that it's direct support for mutual suspicion. And as a mark of how compatible SES is, a lot of the people writing the Salesforce apps, to a first approximation, just think of what they're writing in as plain old JavaScript, and it works. And that, once again, is also reflected in the experience we had at Google with Caja.
Assuming sandboxing of all of the actual code, there are some resource expenditures that this might still permit.
I'm sorry,
there might be resource expenditures that this might permit. So you might be sending code that actually allocates a lot of memory or spends CPU. And so that might still be an attack vector. I wonder if you have ways of statically detecting that, or at least hints, or have an even stricter subset that takes that away.
So let's divide blockchain use from other hosting environments. Let's deal with the other hosting environments first. There is no protection against denial of service by writing an infinite loop. For example, any of these Salesforce apps under the Lightning platform, when run, might just go into an infinite loop and hang the page. Now, the interesting thing is, there's very little benefit to the attacker of writing such an app, and an app that does that when incorporated into a page is going to get unlisted, and people are just going to stop using it. So for outside of the blockchain, the main thing is that there's little to be gained by wedging the application you're incorporated in, and there's a quick iteration where anything that does that just stops being used because it's easy to detect. It's an attack that when it happens, there's no mystery what's happening. You're wedged. Now, with blockchain, we're planning to do the same thing that everybody else does on blockchain, which is essentially a gas model, a metered gas model. Because of the way in which we want to incorporate agoric market-based resource allocation concepts into resource allocation, we've got some additional elaboration of that. But essentially, what the gas model does is an infinite loop just starves that turn. Once the turn is starved, in the blockchain context, everything's transactional. You abort the turn as a whole, and then it's as if nothing happened. So you don't have this world of partially corrupted state that happened at the point you ran out of gas. When you ran out of gas, you just rewind to your last good state.
So it seems like there is a range of approaches to this problem, from something like CloudFlare workers, where they're just using V8 isolation, down to something like Starlark, which is like super crippled Python. And it seems like a lot of these approaches have been kind of dialed in for very specific applications, whereas this one is trying to solve both this like in-browser consumer application kind of task, as well as maybe what seems like a different domain with these financial applications. Can you talk a little bit more about like how you've chosen the parameters?
So CloudFlare is the one that I'm familiar with. Kenton Varda at CloudFlare is very familiar with our work, is very much influenced by the object capability approach to things. And with regard to the overall ambitions of Cloudflare workers, where one of these things running into an infinite loop should not prevent progress on the other ones, for that situation, having these things essentially run as separate threads so that one getting wedged doesn't stop the other was a fine way to run Cloudflare workers. I think that this, in addition, allows a much lighter weight multi-tenancy. In their terminology, SES enables featherweight compartments where each unit of isolation is just characterized by creating a few objects rather than an entire V8 isolate. So we can create much finer grain units of isolation, but where you're not, those finer grain units don't provide concurrency isolation. The Cloudflare workers with their isolates, that's really the smallest practical unit, starting with JavaScript, for doing concurrency isolation. There was a question over here.
Yes. Thank you. It seems, everything you're showing is specific to the Agoric platform, right?
Everything that I'm showing is motivated by explaining the Agoric platform, but the Salesforce Lightning platform builds on the technology that we constructed together, and the Lightning platform itself is not part of the Agoric platform. So and likewise, we're collaborating with Cosmos on creating the IBC, the inter-blockchain protocol. Cosmos has many other plans for the inter-blockchain protocol that are not part of the Agoric stack. So collaborating with things relevant to many other players, but all of which are relevant to the stack we're building.
And would there be steps then to running this kind of logic on top of other blockchains? Let's say something.
Oh, yes.
JavaScript like Lisk or maybe Ethereum also.
Yes.
How would you approach that?
Yes. One of the things that's very fortunate is that Wasm, the WebAssembly, is becoming a standardized virtual machine for new blockchains, and Ethereum, which is the main entrenched case of a different virtual machine, is putting a lot of effort into switching from EVM to Wasm. The XS JavaScript engine that I mentioned for Moddable that's used for embedded, that's actually the engine we're planning to run on blockchain anyway. And that one already has Wasm as a first-class target. So that one is an interpreter, not a JIT. Good luck running JITs on Wasm. That'll never happen. But XS is a straightforward interpreter that compiles to Wasm, and therefore we can run our JavaScript on top of any blockchain that runs Wasm, and we plan to. We have put in a significant amount of effort into running as a parachain on top of the Polkadot platform, and we plan to get back to that.
Slight follow-up to the earlier question. So I think it's in that continuum of non-blockchains to blockchains, we actually think the metering can be extremely useful. So
I'm sorry,
metered,
your thing.
So in the non-blockchain case, I think the gas or metered computation model can be extremely useful for all kinds of applications. So maybe not in the App Store model where you can see that an application is bad, but for example, we would totally embed this kind of thing into things like IPFS if we could meter the execution of a single object in a single method invocation. If you could snapshot the state, run a method invocation, if it fails, just revert back to the prior state without any change, that would be the kind of execution runtime that we kind of seek to enter into. Because certain reciprocal systems won't meter it economically necessarily, but they would be able to prevent all kinds of attack vectors by doing so.
Yeah. Once we have metering in and working, we plan to do it at a level of abstraction such that the metering mechanism is not specific to blockchain, where any other platform running our software, if they're interested in running in a metered fashion, will be able to do so. In particular, we've already talked to Moddable about where you would instrument in the XS interpreter in order to do things like metering. And this will be the last question during this pause, and I'll take further questions at the end of the talk.
So in talking about removing insecurity, can you give some specific examples of features of SES that you remove from Jessie?
Oh, yeah. The most radical thing that shocks many JavaScript programmers that we've removed from SES to make Jessie is this, the this keyword in JavaScript. And as a result of removing this, classes don't make sense. The prototype inheritance pattern for polymorphism doesn't make sense. The objects as closure pattern, which is what you saw with the counterexample, that's what makes sense. So it leads to a very different style of use. That's the most radical change. There's lots and lots of particular things that you're just better off without, double equal versus triple equal. We prohibit the use of switch where you can fall through from one case to another. And we have linting rules that largely enforce that you stay within the Jessie subset. The Jessie subset is advisory. If you leave the Jessie subset, you're still in SES. The object capability rules are imposed on you. We're working with some formal methods people towards formal specification and verification. And the only language that we imagine applying these formal tools to is Jessie, where the Jessie code coexists with SES code, and the formal methods tools have to make that assumption. But if you leave the Jessie subset, then the results you get from the formal analysis might no longer be sound, but might still be informative.